Some things in life are incredibly fast, right? Like an explosion. And some things are incredibly slow, like a nail rusting over years. But how do we actually put a number on that speed? Well, today, we're going to get into the science of chemical reaction rates, how we measure, calculate, and even predict the speed of chemistry itself. So let me ask you a simple question. How do you measure speed? You're probably thinking about a car, right? You just look at the distance it travels over a certain amount of time. Miles per hour, kilometers per second. It's pretty intuitive. But what happens when you're talking about a chemical reaction? You can't just slap a speedometer on a molecule. You can't track one tiny particle from start to finish. So how in the world do chemists do it? How do you measure the speed of something you can't even see? That's the big question we're going to tackle. So here's our game plan. We'll start with the basics. What even is a reaction rate? Then we'll see how the speeds of different chemicals in a reaction are all connected. After that, we'll get our hands dirty with some real lab data, learn how to read the visual story these reactions tell on a graph, and finally put all the clues together to figure out a reaction's master equation, the rate law. All right, let's jump right in. First up, what exactly is a reaction rate? You know, at its core, it's really just a measure of change over time. In any reaction, you've got your starting ingredients, the reactants, that get used up. And you have your final stuff, the products, that get made. The rate is just how fast a reactant vanishes or how fast a product pops into existence. Let's make this real with an example. Here we've got a problem where 23.5 grams of magnesium are used up over 6 minutes. The math is exactly what you'd think it is. You take the amount that changed and you divide it by how long it took for that change to happen. And that gives us our answer, 3.92 grams per minute. See those units? They tell you the whole story. An amount, grams, per unit of time, minutes. That's our speed. Simple as that. But here's the thing. A reaction isn't just one chemical off doing its own thing. It's more like a team sport. So if we know how fast one player is moving, how do we figure out the speed of another player on the same team? And this is a super important question. It's great that we know the rate that magnesium is disappearing, but what does that tell us about, say, the hydrogen gas that's being produced in that same reaction? Is there a connection? Oh, you bet there is. And the secret? The key is hidden right in the balanced chemical equation. Think of this equation like the recipe for the reaction. It tells you the exact proportions. So for this one, it's saying it takes 4 parts NO2 and 1 part O2 to make 2 parts N2O5. That ratio is our magic conversion key. So if we know that oxygen is being used up at a rate of 0.024 molar per second, molar is just a way to measure concentration, we can figure out the rate for N2O5. We just look at our recipe, the mole ratio. For every 1 O2 that gets used, 2 N2O5s get made. So the rate for N2O5 is just going to be twice as fast as the rate for O2. It's a simple multiplication. Okay, that's awesome when someone just hands you the rate. But in the real world, in a lab, you got to figure it out yourself. So let's see how we can go from a bunch of raw measurements to a calculated reaction rate. Here is a totally typical data set. We're reacting aluminum with acid, and one of the things it makes is hydrogen gas. Now, since the gas floats away, the total mass inside the beaker goes down. And by tracking that change in mass over time, we can figure out the rate of the reaction. Okay, first step, what's the total change here? Well, we started at 256.3 grams, and we ended at 254.5. The difference, what we call the delta mass, is 1.8 grams. That's the exact mass of the hydrogen gas that was made and then escaped. And second, how much time went by? That's the easy part. The experiment ran for a total of 6.0 minutes. And now we just put it all together. The change in the amount divided by the change in time. 1.8 grams of hydrogen divided by 6.0 minutes gives us an average rate of 0.30 grams of hydrogen being produced every minute. See, we just calculated a real reaction rate from scratch. Numbers are fantastic, but you know what they say? A picture is worth 1,000 words. Graphing this data can show us hidden patterns and tell a much deeper story about how the reaction is actually working. Now, at first glance, these graphs might look a little weird, but they are based on a really clever trick chemists use. See, if you just plot concentration over time, you usually get a curve. But if you plot the data in special ways, like using the natural log of the concentration or 1 divided by the concentration, you can sometimes turn that curve into a perfectly straight line. And which trick works tells you something really important about the reaction. The type of graph that ends up giving you that straight line tells you the order of the reaction.
So, if plotting the natural log of concentration versus time is what makes it linear, boom, it's a first-order reaction. If plotting 1 over the concentration is the ticket, then it's second order. The y-axis tells the whole story. And what's really cool is that the slope of that line gives you the reaction's rate constant, which we just call k. Think of k as a unique speed fingerprint for that specific reaction.
All right, it's time to put all the pieces of the puzzle together. The ultimate goal, a lot of the time, is to find what's called the rate law, a single, powerful equation that perfectly describes how the rate depends on the concentration of each reactant.
To figure this out, we use something called the method of initial rates. Basically, we run a bunch of experiments, like you see here, where we mess with the starting concentrations on purpose, and then measure the starting rate for each trial. We're pretty much playing detective, isolating one variable at a time to see what it does.
So, our first job as detectives is to isolate one of our suspects. Let's focus on reactant A2. We need to find 2 experiments where the concentration of A2 changes, but the concentration of our other reactant, B2, stays exactly the same. Let's look at experiments 1 and 2. See how B2 is constant at 0.010? Perfect. That's what we want. So now we ask, what happens when we double the concentration of A2? Well, the rate goes from 0.010 to 0.020. It doubles too. So a 2x change in concentration caused a 2x change in the rate. That's a direct one-to-one relationship, and that tells us the reaction is first order for reactant A2.
Now we just do the exact same thing for B2. If we compare experiments 1 and 3, A2 is held constant while B2 gets 4 times bigger. And what happens to the rate? It also gets 4 times bigger. So the reaction must be first order for B2 as well. We take those 2 findings, combine them, and we get our final rate law. Rate equals K times the concentration of A2 times the concentration of B2. We've done it. We've found the reaction's master equation.
So, we've totally cracked the code on how concentration impacts reaction speed. But concentration isn't the only knob we can turn to speed things up or slow them down. What about other factors? What role does something like temperature play? Or maybe adding a special ingredient called a catalyst? That right there is the next big piece of the puzzle. Thanks for joining me.